Our third paper will be presented by Professor Prins. His title is Methanol synthesis catalyzed by calcium and palladium.
Wolfgang, Mr. Chairman, ladies and gentlemen, thank you very much for the introduction. I just want to make a small change from the former speaker. The molecule is one step to the left in the periodic table, CO instead of NO, and the catalyst is two steps in the periodic table, one step to the left and one step down, copper to palladium. So the subject is very similar. Now before, however, I jump into the subject, I want to explain for those of you who don't know the connection between Wolfgang and me what our connection is. Now, Wolfgang had a life before his present life, if you don't remember that, and that was his shell life. And I do not belong to his present life, more or less. I belong to his former life. I joined Shell in '66, but it wasn't, let's say, before '71 that we really met. We were in the same department all the time, but in '71 he became the department head of the fundamental catalysis group, and I became one of his three lieutenants. And one or two of the students already had made remarks about the great impression that a personality like Wolfgang can make on you, and I don't want to dwell on that any more than that. I agree with their remarks. Wolfgang also had a very lasting imprint, as we say in catalysis, on me, and I'm very grateful for that. When years later I was offered the chair of George Schuit, and here is another connection, I'll come back to it, I came to him because I knew that he had been offered the chair first, and I wanted his advice. Should I take it? Shouldn't I take it? You know, I had an interesting and good position at Shell, and should I leave? Should I go back to the university? And I still remember what he said. He didn't give me an answer, yes or no, do it or don't do it. He said, well, why don't you answer the question, are you more interested in power or in fame? So, being interested in both, I went to the university. Then I took the chair, which, as I said, belonged to Professor Schuit, and I'm very grateful that this slide is here. Actually, as you then heard, I have a somewhat difficult relationship, if you want to call it a family relationship, because in a way, although he was not my doctor father, as we say in German, I was not doing his PhD with him, but I was in his group in Shell, so in a way he was my scientific father. But at the same time, of course, when I took over the chair of George Schuit, George was also my father, but on the other hand, as Wolfgang already remarked this morning, George was his father, in a way. So I have a very strange relationship with Wolfgang. Thank you very much. Now thereafter, in our present life, Wolfgang, we still had many contacts. I'm very thankful for that. You moved to the United States, so did George before you, and several times I was visiting you and George, and we always had very pleasant talks, and I enjoyed your hospitality, and so I did at George, so thank you very much for that. Now today I chose a subject which in the old days was very close to Wolfgang's heart, and I still think it is, and that is the Fischer-Tropsch type of reaction. But I want to concentrate on a small piece of it, and that's the methanol reaction. This, let me show who really did the work. Alberto Gotti is the student who did most of the work I'll be describing. Christian Zellmer did and is still doing the XPS work, that is part of it, and Norbert Kruse is here, is also taking part in this investigation. Now it goes back to old work, end of the 70s, by Jules Rabot, who told us that palladium, being in this part of the periodic table, is not very good in dissociating CO. And he had a publication where he showed that palladium on silica was a very good catalyst for making methanol. And he said, gee, see, Palladium doesn't dissociate it like rhodium can do, and therefore what can it do? It can hydrogenate it, and there you have your methanol. A couple of years later, Jack Lunsford with Fadula published, however, that when you take different silicas, you get different results. On the one silica, you can make the methanol, on the other silica, you can't. And then for those of you who have been working with palladium single crystals, you know that you cannot make methanol on a palladium single crystal. So there was a problem. And we have been taking that up again. And since a couple of years, people like Vladimir Ponec and also we have found that you better be careful with certain supports, and especially with silica. With alumina you have less of a problem because alumina in a way gathers impurities, if you wish to call it that way. But silica, you better be careful because impurities may end up very close to your metal because there's no anchor, if you wish, on the silica. So we made our own silica from silan compounds, and we're very careful not to use glass because the sodium and the potassium in the glass can be leached out. So we either used quartz or plastic, and the students had their gloves on, and so on and so on. And when you really do that, you come to the following result. You come, for the rhodium case, you come to something which was already in the literature. It's a good methanation catalyst. You even make acetaldehyde, a little bit of ethanol, you make a little bit of ethane, and you make a very tiny bit of methanol. Be careful, this is a logarithmic scale. You see it's 2.5 orders different between the methanol and the methane. Now the palladium on this very pure silica is a very bad catalyst. It's low in methane, it's of course much lower in the C2+, and it's also very low in the methanol. And actually I think that this little bit of methanol is just the last little bit of dirt which is still on this catalyst. Because of many articles suggesting that it's important to look at the precursor, we had a very close look at the precursor, and in our hands there is no difference between a rhodium nitrate and a rhodium chloride if you really do the work careful and if you really take a pure silica. So part of the answer why some authors come to different results may be in the impurity on the silica. So this is hydrogen over rhodium. The dispersion was the same here, just to cancel that effect out. The same for palladium. Although we had 3 salts and there's a different dispersion, very low, reasonably good, and almost equal to that, there is a difference in the methane and the C2+, and that depends on the dispersion. And the reason is, of course, that we know that palladium is very bad in dissociating CO. Only when you go to very small particles, or you go to king sites on a single crystal, then you can dissociate CO. And that's why on the much higher dispersed palladium, you can dissociate the CO, and you make somewhat more methane and C2+. Look at the methanol, it's equal, and it's very low. So still, it doesn't matter actually which salt you take. Now then it was obvious that it must have to do with something like an impurity. So one of the best in our hands was calcium, and here you immediately see what happens. You take a palladium on a very pure silica. This is, the impurity level is down to the ppb level. We checked it with ICP. When you dope it with calcium, and this is something like 1000 ppm, which is like 0.05 calcium versus palladium. I'll come back to it. You see that the methanol shoots up almost 2 orders of magnitude, and the methane and the C2+ are suppressed. Here is a slide with this as a function of the calcium loading, and also you see it for the rhodium. Let's look at the calcium first. The methane was low in the first place, so you suppress it, and then you are at a constant, very low level of methane, and the methanol goes up, and there it's constant. And this means that you can, on this catalyst, run and make methanol at 99+% of methanol. The rhodium starts with a much higher level of methane, of course, and you can also suppress it, but not so deeply as the palladium. And the methanol goes up to, as you see here, almost the same level. The dispersion of the catalyst, this catalyst was a little bit better dispersed than that one, but the difference was not much. So this catalyst only has 90% selectivity. Also note that you need somewhat more calcium here to really be in the constant area than for the palladium. So we studied several other promoters. And here's a whole series. The alkali metals and the earth alkaline metals and one or two others. And you can see that it's not only the calcium which is doing a good job, but the lithium is quite good, and then you go down. This was already seen by Professor Tamaru in 1981. He had a publication in Transaction of the Faraday Society where he started with the lithium, sodium, and so on salts of the palladate, and where he showed the same trend. You see that the trend here is different. The zinc is very low to our surprise, but don't forget this is not zinc oxide, this is zinc added this amount on the silicate. And then the lanthanum is also very good, but the lanthanum is the exception here because it does make quite a bit of methane. It's the only one which improves even the methane make on the palladium. We have no explanation for that yet. All the others suppress it like I showed for the calcium. When you look at a few results for rhodium that we have, we didn't study that in such a great detail as the palladium. Originally, without any promoter, the methanol is low, there's a lot of methane. When you come with something like calcium, you go to more or less 1-to-1. You, as I showed you, you also promote the methanol in this case, but depending on the loading, this loading was not very high, you can't suppress the methane very much, and the sodium and potassium are no good. The iron, of course, that has been discussed heavily in the literature. In this conference, we had the iridium iron on magnesia, amongst others. And you see that the iron also makes a lot of methanol, but depending on your loading, you can still make a lot of methane. What about the explanation? Well, the more or less established mechanisms that are available in the literature, I have nothing new to offer there. There are actually two sort of routes. CO adsorption, and you can make a formyl intermediate, and then you go to a sort of formaldehyde intermediate, to methoxy, and eventually you end up with the methanol. Or one way or another, be it through the CO plus oxygen or the CO2 directly, or the CO plus an OH minus group, you go through a formate, which was suggested, as far as I'm aware, for the first time in that 1981 paper by Professor Tamaru. And then you go all the way to the methoxy and so on. This is seen from the molecule point of view. What about the catalyst point of view? What are the mechanisms in the literature? Now, one which Professor Ponech favors quite heavily, and it's unfortunate that he is not here, I would have enjoyed a good fight with him, is the formyl intermediate. And his suggestion is that formyl is made on a cation. So if this were the red one were palladium, then he assumes that this is palladium plus, stabilized by an oxygen from the promoter, and that's then doing the job, and that goes through the formyl. There are other suggestions. Then the other three are all going through the formate, and then there's one suggestion, and this is then again by Tamaru, is that the promoter oxide, so the calcium oxide is, for instance, on top of the metal, and that an oxygen atom from there gives you the extra oxygen needed to make the formate, and from there you go and hydrogenate it. A slightly different mechanism is that the promoter oxide is sitting next to the metal on the support, but this is more or less semantics, I would say. A really different mechanism is where the promoter oxide is really separated from the metal, and now you really make the formate on the promoter oxide, without any palladium or copper or whatever metal have you taking part in the formate formation. And then the question is, how is this hydrogenated to the methoxy and then onwards to the methanol? Is that by spillover of hydrogen in that direction, or is there a spillover of the formate to the metal and then the hydrogenation? Or is there a third route? In this case, of course, if this is very close, you can have the hydrogen spill over that way or the formate spill over this way. You can still believe it more or less. A slightly different mechanism is through the gas phase. And that goes as follows. I recall that in the old days, methyl formate was made in the industry by sodium hydroxide. No metal needed. What you did is you took your sodium hydroxide, you had carbon monoxide, and the idea was that you're making a formate, and then with methanol you're making methyl formate. Now, what about hydrogenolysis? Suppose this is going through the gas phase to the metal, and then you get hydrogenolysis, and then you get two methanol molecules. And your only problem is how to make the first methanol molecule. In the industry, they just added the methanol, and then of course in this step you get the methyl formate, and there you go. In our case, all it needs is a very slow site which starts the cycle, and then you have photocatalysis, and then the mechanism would be that you make your formate here on the promoter metal oxide, on the calcium oxide for instance, and then you make a methyl formate. This goes through the gas phase to the metal somewhere. Doesn't matter if it's close or far away. Then you have the hydrogenolysis there. So the only function in this case of the metal is to deliver hydrogen atoms, do the hydrogenolysis. Well, at the moment we have no answers because this study is just 1 or 2 years underway. We do have an answer, however, on the question, is it a CO or is it a CO2? Because for those of you who are very familiar with the copper, and he is an expert who worked on the copper a long time ago already, and for a long time, and there are many others were in this conference debating again the copper issue. And we all know that in the copper case, by now at least we know that the system doesn't go through the CO. It's not this reaction, but this is the Brutto reaction. You start with the CO2 actually, and it's the CO2 that goes to the methanol. However, the water with the CO gives you the water gas shift reaction, and you get the CO2, and the cycle is closed. So Brutto reaction is still this, but it goes through the CO2. Now in our case, that's absolutely not the case. It's well known that if you take a pure copper, for instance, Alex Bell and his student Clark did this, you take a copper on silica with CO alone and hydrogen, you have a very low turnover frequency to the methanol. When you take the CO2, it's very much higher. In our case, the palladium alone on the silica, it does show with the CO2, it does show CO, so you get a somewhat of an activity for the water gas shift, for the reverse water gas shift. But there's no activity for the methanol. So it's not comparable to the copper case. However, if you promote it with these basic promoters, then the water gas shift goes up tremendously, and at the same time you see methanol formation. So that brings me to my final slide. I summarize a few of these examples here. The palladium on silica is having a low activity, very low activity for the methanol, but the moment you promote it with a basic promoter like calcium or lanthanum, the earth alkaline or the alkaline metal oxides, it's very good. When you do that with, let me show this. When you do that with CO2, you see that the palladium on silica itself is not good. But when you then promote it, it's good again. And this in contrast to what you get with copper. With copper and CO, it's low. With CO2, it's higher. And in all cases, it does promote it. But the palladium absolutely is not the same as copper. It is really going through the CO, and it is heavily promoted by a basic metal oxide. And at the moment, we are trying to study with the XPS and the like where it is. Is it sitting on the support? our feeling is yes, indeed, the majority of the calcium and the other promoters is on the support, but some of it is on the metal as well. I didn't tell you yet that when we study the palladium and we put a lot of calcium oxide on, the hydrogen dispersion, the hydrogen absorption, goes down. And the way we prepared the catalyst was to always start with the palladium, calcine it, and only then come with the promoter to ensure that the palladium size is always the same. And when we then put the calcium on, the hydrogen absorption goes down, showing that some of the calcium is on the palladium. So our feeling is that it's mainly the calcium oxide on the palladium which is doing the job. Thank you.
Questions over there?
About the role of your additive in the metal. There's of course a parallel with all those bimetallic studies that many of us have done. And I wonder if not one explanation could be that CO on rhodium, iridium, it doesn't matter what you take, that CO binds just too strongly there and doesn't give the hydrogen a chance.
Yeah.
Now, if you put promoters on the surface, it may be that you block certain sites for CO, but just leave room for hydrogen.
Yeah.
In the case of iridium, this is iron and so on, we have clear indications for that. So my question would be, have you looked at the kinetics? Do you see something like a changing order in hydrogen when you add promoters?
We are setting that up right now. I agree. The only function left of these metals, and I showed you that rhodium is as far as the methanol is concerned, is exactly the same as palladium. It looks like all these metals that we have studied, what is left is a hydrogenation function, nothing else. You suppress the CO dissociation by covering it. And yes, the idea is you can cover it with something like a metal, like iron or anything like you did. In this case, it's calcium or anything like I showed. But the question is, of course, now, this would suggest that we should cover it with something very innocent, which cannot be basic or acid. So that, and then the question is, can you still make the methanol? Because your suggestion is that you're still making the methanol on the metal and you don't need, I mean, that's what I sort of taste behind your words, yet you don't need a basic promoter at all.
I don't want to
You are just
about
blocking.
the mechanism. I mean, that's the second step.
Yeah.
But just the role of hydrogen is something that a lot of people have not paid attention to. So I wonder if that would play an important role. And after that,
Yeah.
you can talk about
Yeah, but I mean, when you think about it, the copper, it fits exactly in this scheme, right? I mean, what the copper does actually, in my mind, is doing the same as we suggest that the palladium is doing. Go through a formate route, that's more or less established. There's not much quarrel about it there. The only difference is the copper versus the palladium is that the copper itself can be oxidized on the surface. And you can make some sort of copper oxide or whatever have you, or oxygen adsorption is much stronger, put it that way. And that means that you have your basic sites already on the copper itself. And on the palladium, that's much more difficult. So our suggestion is that's why you have to come up with calcium. And you can't do it with the palladium and the oxygen alone. So, but your suggestion is well taken. It means we must try to block it with something very innocent, which by itself can never take part in the catalysis. And then it's only the suppression of the CO dissociation on the one hand and giving the hydrogen the full chance to do the CO hydrogenation.
The methanol is still the easy part of the problem, but the real problem starts when you work with rhodium and some promoters, and the major product is ethanol and ethyl acetate. I wonder, from the mechanism which you had in the blackboard, you seem to have a light penchant for the idea that the formate is basically on the oxide, and the palladium is just paid to furnish the hydrogen atoms.
Right.
Now, if one follows this line, one could say the rhodium is paid to furnish the methyl group, which sits on the formate, and then later the hydrogen atoms to produce the acetate. Indeed, there is indication that the acetate is the intermediate for the ethanol, because ethyl acetate is the other product. And what you have intuitively assumed and not even discussed is something which we can confirm on the zeolites with a lot of work, that it is not an interaction between the ion and the metal, but it is the oxide and the metal which do it. So in our case we use manganese. We have speculated for years whether manganese ions could interact with the rhodium and or with the CO at the oxygen end, and Horacio, who is here in the room, has disproven all that. It is clearly that you have M&O particles which are presumably in contact with the rhodium particles. So is that then your suggestion, that instead of the formate you make the acetate sitting on the manganese oxide and then finally it is hydrogenated, or how does the next extrapolation from your work look like?
Well, we haven't addressed that question at all. We are working on methanol, not on acetate or ethanol. We did it years ago, but we haven't followed up on it, so I can only speculate. And yes, probably you may be right. I don't know. I have no answer to that. I haven't thought about it. We fully concentrate on the methanol now.
Question?
In the frame of the interpretation of the promoting effect of the alkaline earth metals you discussed, I have some difficulties in understanding to which properties of this material we have to relate these properties as it's going through a maximum. There is no continuity from magnesium to barium. It goes through a maximum.
You are right. It's very difficult to address that question. We should do a lot more work to really answer questions like that, because and that's why we must do more fundamental work, let's say, with foils and single crystals and like that. The problem is that there are at least two effects. One is, let's say, an electronic effect going from lithium to cesium or magnesium to barium, right? And then you ask yourself your question, why is it going down here? Why is there a maximum there? However, this is, let's say, convoluted with the other problem, that is diffusion over the surface. If we assume that these promoters must be close or on top of the metal, you must ask yourself the question, how do they come there? How do we prepare our catalyst? The answer is, we make a palladium or silica catalyst and we impregnate it with a solution containing the nitrate of one of these salts. And then the question is, does it really reach the metal? And it may well be that the product of the two is somewhat more complicated than just thinking like, oh gee, lithium is like magnesium, and why doesn't it go down or why doesn't it go up? I must point out that it's not uncommon in the stability of metal oxides and metal silicates that there is a maximum in this series and there is no maximum here. So this has to do with Born-Haber cycle. So I mean, it could be that that has to do something with it. That you are making, you are having an interaction, and so you're making a mixed oxide partly, and then you decompose it again. So you have to think about Born-Haber cycles. But let's forget about that. At least these two factors, like the electronic effect and the diffusion, makes it already complicated. We must split that up and study.
There is one similarity between the copper and the palladium system that you did not allude to, namely that the copper catalysts are also promoted by base, by alkali.
Yes, true.
And that is for CO, not CO2 hydrogenation, and also water promotes that reaction. And at the same time, the forward shift reaction between CO and water is also promoted by alkali. If you keep the temperature low enough, then the catalyst still remains 99% selective for methanol. So you did have a picture in your mechanism of the CO insertion. You alluded to that as a very old reaction, insertion of CO into OH group. That would be the part of the cycle that makes formate from CO. It does happen on copper. The promotion effect is not small it's a factor of 2.33. You can interpret it as 233%, and it's been patented. The difference between the palladium promoted by divalent and the monovalent, the inactivity of the monovalent, may be an effect of dispersion, because you might think that the monovalent alkali hydroxides, the most basic of which would be cesium hydroxide, would be the best promoters. In your case, they are not, but in the case of copper, it is the best promoter.
Yeah.
It's better promoter than calcium and barium oxide, because these agglomerate. There's evidence for that, and so one has to control the dispersion as well in submonolayer and interdispersion of the two, the hydrogenation function and the basic function. But both catalysts do have a similar feature in that they are a combination of base and hydrogenation catalysts.
Yeah, I agree. I agree completely with all you're saying. Again, the system is more or less similar. The only difference is that the copper can be oxidized or absorb oxygen, and that's the additional feature in addition to what the palladium
Oxidized
has.
more easily than
Yeah.
palladium.
I see many hands on this side and the other side. So one short question.
The trend of the effectiveness of the methanol's promotions depend on the oxidation, the ions from the metal plus one side, metal 2 plus 2 stage. Should be oxidative ions stabilize the oxidative palladium or some oxidative copper, which could be active for thermosynthesis. So might be
This is, you mean,
promoters.
the palladium could stay like 1+?
Plus.
Yeah, like the Ponich idea.
It looks like that.
Yeah, and then you go through the formula if you wish.
Because you know,
Actually, the whole reason the whole reason behind this study is we switched to palladium instead of copper to get away from that copper discussion, because the copper is too easily oxidized. The palladium-1 chemistry, as far as I'm aware, is only when you have organometallics, when you have really ligands like phosphine and the like. And in the good old hard inorganic chemistry, when you have only oxygen there and chlorine or whatever, and that's gone anyways, we proved that. It's very hard to believe that you have a palladium-1+. So, I mean, the difficulty in catalysis is IDs will come back and forth every decade or so, I agree. And in the end, it's extremely difficult to disprove an ID, and so I can't really disprove palladium plus, because it's so difficult to detect. And yes, you could say, okay, suppose there was just a little bit of palladium plus, and suppose that was extremely active, and couldn't you then explain all your results? The answer is yes. You have to say yes to questions like that always. But it's not reasonable.
Okay, I think we have to start with this section. We will have 20 minutes break. So we will resume at 3:40.
When will the video be shown?
It was